We now need to discuss the way that memory is organized and the way that it's allocated for variables, and it's not exactly straightforward. So far, we've had very simple bindings like, for example, let x equals 5. What this means is that somewhere somebody is allocating an i32 variable, so 4 bytes are taken. But where exactly? Well, if you think of the memory that's being used as a kind of contiguous area like this, then there are two ways we can start allocating the memory that's available. We can do it from the bottom, or we can do it from the top, and in fact that's how it's typically done. The bottom part is called the stack, and the way that memory is allocated on it is fairly straightforward. As you allocate something in the following fashion, you simply allocate a chunk of memory. Subsequently, when you have another variable, you have yet another chunk of memory for that variable. And these variables, they contain the actual values. So this variable will take up 4 bytes and it will contain the value 5. This chunk of memory would contain the value 32 and so on. And this is all stack allocations. Now, the great thing about the stack is it's a kind of last in, first out structure, meaning that as you put things on top of the stack, you can start getting rid of them in the reverse order and effectively removing them in the sort of popping the stack, removing the last element until you have nothing left. Now, the stack is used obviously for these kinds of allocations. It's also used for situations where you call functions, because when you have a function and it takes a bunch of arguments, all of these arguments get put on the stack, and subsequently when this function, it might be calling another function with g of z, the z will also go on the stack, and so would all the local variables like these that the stack is used for. And subsequently, you can unwind the stack and get rid of these variables. So this is very easy, and one of the consequences of this is that we don't really have to deallocate this memory explicitly, meaning that after I invoke a let binding, after I do let x equals 5, I don't have to delete the x explicitly. I don't have to say x.drop or something like that at some point for the memory to be deallocated. So the key things about the stack is it's fast, but its size is limited typically. So you cannot allocate, an infinitely large array on the stack because, well, the stack has a certain limitation. The other choice of allocation, dynamic allocation, is called the heap. And the heap is up here. So the heap works kind of differently in the sense that you have a chunk of memory. So you have a chunk of memory and you can allocate things for long-term storage. So the stack is treated as a short-term storage structure and the heap is treated as a more long-term storage. So how do you allocate things on the heap? Well, the way you do it is by using something like the box type. So instead of doing let x equals 5, you effectively say let x equals, and then use a box, and the box is a generic type, but here we can say box new with a value of 5. So what does this mean? What does this actually do? In actual fact, what we end up with is we end up with something like a reference or a pointer. So essentially the box itself is still here somewhere on the stack. Let me get rid of some of these so that we get more space for writing. So the box, the variable x that we have here would still be on the stack. The only issue is that its value, instead of having a physical value of 5, it would have an address which points to somewhere on the heap. It would have an address of this variable. And this variable, in turn, is the variable that actually contains the value of 5. So what does this mean? Well, it means that in order to access this variable, like let's say we want to print out a 5, instead of doing a print line, let's do it correctly. So instead of doing it like this, comma x, you have to follow the memory address that x points to. And for that, we use the dereferencing operator, which is the star. So you would write print line and then star of x. So essentially, the box construct, box of t, allows us to heap allocate variables for longer term storage, shall we say. And we can certainly figure out how much memory the allocation actually takes up on the stack and the heap, and we'll take a look at it right now, because it's time to leave this nice drawing application and jump into code. Alright, so let's begin by setting up a small scenario. Now, I'm really fed up with just reusing this particular module for like everything. So I'm going to actually make a separate module specifically for our stack and heap demonstrations. So for that, let's make a new file here. I'm going to add a new item. It's interesting that I don't get the usual. Yeah, here we go, module. So I'll just call it SH, short for stack and heap, like so. So this is going to be not much interesting stuff here. I'm going to disable dead code. Dead code like this, so that I can have some, and then I'll have a public function. Sorry, that should be a public function called stack and heap. There we go. Okay, so inside the main, all I have to do is comment out. Well, I think I've already commented everything out. So let's just have sh stack and heap, and we'll continue our work in this file. All right. So what is the deal with the stack and heap allocations? Well, let's try to set up a scenario by first of all, let's have a structure for storing a point. Now, I know we haven't covered structures yet, but in large portions of this course, we're going to see constructs ahead of time. So let's just assume that there is this construct called point, which is a custom data type which has x and y coordinates. So let's just have y and x. Okay, so I have this idea of a point, and I have different ways of allocating it. I can also return it from a function, for example. So I could have a function called origin like this, which would actually give one of these points. So I might return a point which is at 0, 0, because that's where the origin of the coordinate system is. So I might return a point with x having the value of 0 and y having the value of 0. Okay, there we go. Okay, so now we get to experiment with this point. So I can make a point, let's say P1, and I can say that it is taken from this origin function. Now, I could do a type declaration here. I could say that this is explicitly a point, but I'm not going to. Let's just keep it as is. So this is an ordinary point. It's obviously stack allocated at this particular instance. Now, what I can do is I can also heap allocate a point in a similar fashion. So I can let P2 be the same point, but I'll allocate it on the heap as opposed to the stack. And the way we do it is with box new. So you just call box new, and then you call, say, origin as before. This effectively gives us P2 as a pointer to some location where the point is actually stored. So these things are somewhat different. And now we can find out how much memory, for example, the points occupy on the stack. So we've used that before. We've had this mem import, std mem. So let's use it here. Use std mem. And now we're going to find out how much the points take up on the stack. So let's output this. So P1 takes up this many bytes, and that's mem size of val P1. Okay, so let's find out how much P1 takes up. Oops, use of undeclared module. Oh yeah, we forgot the module statement, of course. Mod sh. There we go. Right, inner attribute not permitted in this context. Well, maybe it's supposed to be before. like this. Okay, let's try this. Yeah, so P1 takes up 16 bytes. Why does it take up 16 bytes? Well, we have some memory like X and Y, and the size of F64 is 8 bytes, and the size of this F64 is also 8 bytes. Therefore, we take up 16 bytes in total. There is no overhead, basically. Now let's talk about P2. So how much memory does P2 take? So here we simply specify, the same thing with P2, and we can run this and see that P2 actually takes up 8 bytes. So why does it take up fewer bytes? Well, because remember, I'm running this on a 64-bit system. So all that a pointer to the origin, a pointer to an actual point, has to do is store the address of where the memory is actually kept. And the address takes up, 64 bits, which is 8 bytes, which is why we get the value 8. So on the stack, we've only taken up the usize amount, whereas, of course, on the heap, we've taken up 128 bits or 16 bytes. So this is how it goes generally. So let's talk about a few more important things. First of all, how do you get the boxed value onto the stack? How do you get the boxed value back onto the stack again? If I want P3 to have the value of P2 on the stack, then I simply follow the pointer. I put the star in front and I say P2. So what's essentially happening is the star in front lets you follow the pointer. It lets you follow where the boxed value actually lives and assign it to a variable. So now I have P3, and I can even try to print line, for example, P3 dot the x coordinate, for example. So that will give me a 0 here. So this is how you follow a pointer. Effectively, it's unboxing. So here we're boxing a value, we're relocating it to the heap, whereas in this location, we're relocating it back to the stack.